This video shows another example of determining the function of the infiltration using Phillips model. You are in hydrology. A record of infiltration capacities was provided, where we are to determine the function of the dataset by the Phillips model format. As like the others, time is taken as x, the independent variable, and infiltration is the dependent variable. So how do we create the function for the dataset? We learned from numerical solutions that given two variables, we can look for the function using curve fitting with the best fit line. By best fit line, we use the slope-intercept form. Y is equal to mx plus b. However, the instruction states that we are to have the function through Phillips model, which is the infiltration capacity as half of S times t raised to negative 1/2 plus k. In order to have the slope-intercept formula be configured into Phillips equation, we check analogous parameters, like y is equal to f of p, m is equal to half of s, x is t raised to negative 1/2, which is then simplified as 1 over the root of t. Then b is equal to k. Having completed the comparison, we can then look for the function of the best fit line using the parameters y and x. From the analogy, we can start looking for the values of y, where using the dataset, we determine the infiltration capacity f of p. Field capacity f sub p has the unit of millimeters per hour. So from here, we can deduce that the numerator requires incremental depth, and the denominator is hour, which is also the incremental time. From the table, the second column keeps the infiltration depth in millimeters. This is then ready to be used for the numerator, incremental depth. Next is to figure out the denominator. The dataset has time, and if one analyzes the values under time, the values have an increasing trend. So we can deduce that this column is for accumulated time. But what we needed is incremental time. Thus, the next column for the table is for the conversion of accumulated time to incremental time. This is done by taking the difference of the time values. First is 1 plus 0, giving 1. Next is 2 and 1, which is then 1. The difference of 4 and 2 is 2. Then, 5 minus 4 is 1, followed by 7 less 5, which is 2. Next is 8 minus 7, which is 1, followed by 10 less 8, giving 2. There is also 11 minus 10, which is 1 again. Then 12 minus 11 also is 1. And last is 15 less 12, giving 3. Now we have incremental depth and incremental time. We can now compute for the incremental infiltration capacity F sub p, which is the ratio of the depth and time. From the first hour, F sub p is 6 divided by 1, which is 6. Then 5.5 over 1 is still 5.5. There is also 6.2 over 2, which is 3.1, followed by 7.1 upon 1, resulting to 7.1. The next is 5.7 over 2, which is 2.85, and 5.9 divided by 1 is still 5.9. Then we have 5.7 over 2, which is 2.85, and again 6 upon 1, and that is 6. Then 5.9 divided by 1 is 5.9, with 5.8 over 3 as 1.93. These are the infiltration capacities, which are the y values for curve fitting. We then compute for x, which is the reciprocal of the square root of t. From the various columns we generated, which one should we take to solve for x? Note that the x-axis is the increasing time, so we use the cumulative time in hours. Starting with the reciprocal of the square root of 1, which is also 1. 1 all over the root of 2 is 0.7071. 1 upon the root of 4 is 0.5. 1 upon the root of 5 is 0.4472. 1 divided by the root of 7 is 0.378. 1 divided by the root of 8 is 0.3536. 1 over the root of 10 is 0.3162. 1 upon the root of 11 is 0.3015. 1 all over the root of 12 is 0.2887. Then lastly, the reciprocal of the root of 12 is 0.2582. These are the values of x in the graph, and y is the incremental infiltration capacity. Although not necessary, we plot x, which is the reciprocal of the root of t, versus the incremental infiltration capacity, y. The first point is 1 and 6, followed by 0.7071 and 5.5. Then there is 0.5 with 3.1, and also 0.4472 with 7.1. Next are 0.378 and 2.85. Then also 0.3536 with 5.9. The next point is at 0.3162 and 2.85, followed by 0.3015 and 6. Then the last point has 0.2887 with 5.9 and 0.2582 with 1.93. The points are scattered, but what we are to take is the best fit line. Then use the slope-intercept function. There are different methods in curve fitting, but we use the principle of least squares to easily solve for the coefficient only by using the functions for slope m, which is as shown. We have x and y, and we can easily take the summation of each column. However, there is a parameter summation of xy from the function. So we compute for xy by multiplying the two columns. Multiply 1 by 6, which is 6, all the way to the end with 0.2582 times 1.93, giving 0.4983. Going back to the function, we also have to solve for the square of x. So add another column for x squared, and compute for the inputs from the square of 1, which is 1, to the square of 0.2582, and that is 0.0667. So take the summation of each column, where x has 4.5505. The summation of y is 47.13. That of xy is 22.6893. And the summation of x squared is 2.5588. We can then compute for m by placing the number of entries, which is 10, multiplied by the summation of xy, that is 22.6893, minus the summation of x, which is 4.5505, times the summation of y, which is 47.13. These are all divided by the number of entries of 10, with the summation of the square of x, which is 2.5588, minus the square of the summation of x, and that is 4.5505. The slope is solved as 2.546610711. We take the long decimals for now, as m is used to solve for the next function. The y-intercept b is computed as the summation of y minus m times the summation of x all upon n. B is then 47.13 less the long number of m multiplied by 4.5505 all upon 10. This gives 3.5542. So the best fit line has a function of y as equal to 2.5466x plus 3.5542. After figuring out the function of the best fit line, y as equated to 2.5466x plus 3.5542, configure this according to the parameters required by Phillips model. That is f of p as equal to half of s multiplied by t raised to negative 1/2 plus k. As both equations have the same configuration, we can easily see that 2.5466 is equal to half of s, thereby giving s of 5.0932. Then the other variable is k, which is 3.5542. So Phillips model for the dataset provided is f sub p as equal to 2.5466 times t raised to negative 1/2 plus 3.5542.